Come on in and don't be late. Let's learn science with Mr. Ed U Cate. G'day students, well welcome to another YouTube video. This is week 3 and not only is it a new week but it's a whole new unit. We've looked at unit 1 and 2 last year, started unit 3 last year, we've just finished unit 3 and we're going on to unit 4, our last unit for the 2 years of our course. And this unit title is Structure, Synthesis and Design. And most of the chemistry that you're going to be looking at in this particular unit is organic chemistry. Don't know about you, but on the weekend I did a lot of this. When the restrictions were lifted and we were able to go out and have picnics in the parks, I took with me one of these to have to cook up my lunches and have a cup of tea with, to boil my water. This is a gas bottle, gas canister. It's made up of a mixture of these 3 gases here: butane, isobutane and propane. Butane has 4 carbons, all single bonds and 10 hydrogens. Isobutane, same number of each of those elements, but the carbons are arranged differently. And in propane we've got 3 carbons and 8 hydrogens, all single bonds, and they're all saturated. So a little bit of that is a revision of last year, but we're going to really get our teeth into that in this next unit, chapter 9. Chapter 9 is titled Structure of Organic Compounds. We're going to have a lot of fun with it. But just a few more molecules in the meantime. Look at this one. You're going to be playing with these kits. Remember the Molly-Mod kit? This one is ethane. Remember the Molly-Mod kits? The black balls are carbons, and the grey links are the bonds, and the white balls are hydrogens. This one here is ethine. Ethine, it's got a triple bond there. Can you see it? This one's propane. Propane's got 3 carbons and it's got a double bond. Can you see that one there? And this one's pentane. The hydrogens are missing, but that's okay. We often depict some of these molecules without hydrogens. We just assume that they're there. We're going to be doing a lot of that next week when you first come back. A lot of model building. I'm just excited. This is going to be a ripping unit. We're going to have a lot of fun. We're going to get on our hobby horse about environmental issues and whether it's possible to make plastics green friendly. It's going to be great. And you're going to be there. Yeah. Yoo-hoo! We're in chapter 9.1 now, hydrocarbons. And some of the things we're going to be learning about in this video, in this section, is the nomenclature of simple hydrocarbons. Nomenclature just means the principles of naming, the naming rules. And we're going to be looking at the types of bonding present in hydrocarbons. And we're going to look at the level of how the level of branching affects hydrocarbon nomenclature. So it should be a real cracker. Well, the main thing that's common to all organic molecules are these hydrocarbon bonds, a bond between carbon and a hydrogen. And here's an example here of pentane. Pentane is C5H12, 5 carbons, 12 hydrogens, 1, 2, 3, 4, 5 carbons, and 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens. Here's the plain way of writing the structural formula for pentane, and this is the Molly-Mod kit version of pentane. Now notice how the carbons are arranged in a zigzag pattern in its 3-dimensional molecular state compared to our 2-dimensional depiction of it just in a straight line. You can draw it as a zigzag if you want, but most of the time we just draw it like that. Now, the naming of pentane is mainly determined by the number of carbon atoms present in the main chain, 5, hence pent, and the type of bonding that exists between the carbon atoms, and they're all single bonds, hence ane, pentane. And also pentane is made up of a main chain, what we call a main chain. We used to call them the parent chain. This main chain is another really important part of the naming of pentane. And our learning of Lewis structures come into all of this too when we draw Lewis diagrams, electron dot diagrams for hydrocarbons. Carbon is from group 14. Okay, it has 1, 2, 3, 4 electrons in its valence shell, in its outer shell. And hydrogen's from group 1, of course, so it's got 1 valence electron. So if we were drawing the electron dot structure for carbon, it'd look like that. It's got from group 4, it's got 4 valence electrons, and each of these hydrogens I'm about to draw has got 1 electron in its valence shell. So when those electrons, when those hydrogen atoms are bonded to the carbon, everything's all happy. They follow the octet rule. So if I was drawing CH4, which is methane, it would look like this. This is the electron dot structure for methane. Carbon's got 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in its valence shell now. Remember, 8 is stable, or 2 is stable. In the case of hydrogen, 2 is the stable number for hydrogen. So let's get into the really exciting part of organic chemistry known as nomenclature, naming organic compounds. Like, here's an example here. This molecule here is 3,4-dimethyl-hex-2-ene. But how do we come up with that name for that particular molecule? Well, there's an organisation by the name of IUPAC. IUPAC stands for International Union of Pure and Applied Chemistry. And they're an organisation that came up with a distinct list of rules to do with naming. This molecule, for example, I should have researched this, but it might have had a common name once upon a time. But the problem was this molecule, such as this, might have had 5 or 6 common names. But this name, no matter which part of the world you're from, is the internationally agreed upon name. Well, let's start with one of the rules. One of the rules to do with naming has to do with the number of carbons in the main chain. And this is on page 220 at the bottom. So let's take this molecule, for example. This is pentane. It's called pentane because there are 1, 2, 3, 4, 5 carbons in it. Pentane. We'll worry about the ane part later, but essentially the prefix for most molecules, most organic molecules, is an important part. The prefix has to do with the number of carbons. So here we go at the bottom of page 220, and it says that the name of a hydrocarbon includes the number of carbons in the main chain, and that this number is represented in the name by a prefix. And here's the list of prefixes over here that you might remember learning last year in table 1. If the main chain has only got 1 carbon in it, the prefix for the main chain is meth. If it's got 2 carbons, eth, 3 prop, 4 bute, 5 is pent, 6 hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. So from 5 down, it's pretty straightforward. Most people know, you guys will know that pent is the word for prefix for 5, and so forth from 6 to 10 carbons. They're down easy, but what about the first 4? Meth, eth, prop, and bute. Well, as it says over here, you've just got to learn or memorize those terms for the first 4 carbons. And last year, I think I might have told you a way that I remember it. It's about my imaginary friend Mep, how I met him at the BP. Mep, as in M-E-P, met him at the BP. Mep, BP. I don't know. Works for me. You can come up with your own. But I mean, it doesn't take long before you memorize them anyway. Meth, such as methane, ethane, propane, butane. So let's have a go at naming our first hydrocarbon. Let's start by finding out the main chain. This is the main chain of carbons. And let's see how many carbons there are in that main chain. There's 1, 2, 3, 4, 5, 6, 7 carbons in the main chain. So the prefix is hept. Hept. And so let's look at the bonds now. The bonds between each carbon are single bonds. You won't find any double bond. Double bond, remember, looks like that. Triple bond looks like that. Single bonds like that. Whether they be vertical or horizontal, it doesn't matter. They're all single bonds. So therefore, the suffix, the part of the word that ends in the word, will be ane, because there's only single bonds. The name of the molecule is heptane. Another thing to consider in naming hydrocarbons is the type of bonding between carbons in the main chain. This is on page 221 that we're up to. There are 3 types of bonding between carbons in the main chain. There's single bonds. There's double bonds, indicated by the little double line there. Double bonds. And there's triple bonds. Single, double, and triple bonds. If there's only single bonds in the main chain, you've got an ane. The suffix is ane. And if there's at least one double bond in the main chain, the suffix is ene. It ends in ene. And it ends in ine if there's at least one triple bond in the main chain. So prefix, you know about a prefix. It's a small word that starts a word. It's a part word that starts a word. A suffix comes at the end of a word. Ane, ene, and ine. Here's an example. If we were to draw bute 1-ene. Bute, there's 1, 2, 3, 4 carbons in the main chain. It ends in ene, so there's at least one double bond. We'll deal with the one in a second. There's at least one double bond, so there you have it. That's how you draw bute 1-ene. And don't forget, there needs to be only 4 lines, 4 sticks, 4 bonds going out from each carbon. That carbon's got 4 sticks coming out. That one's got 4 sticks. This one, 1, 2, 3, 4. And this one, 1, 2, 3, 4. That's bute 1-ene. If I was to draw bute 1-ine, that would be likewise. Bute has 1, 2, 3, 4 carbons. There's at least one triple bond because of the Y and E suffix. And remember, every carbon's got to have 4 sticks coming out. Remember what a stick is. A stick equals 2 electrons, a covalent bond. Remember, hydrocarbon chemistry, organic chemistry is all about carbon bonds. intramolecular bonding. Covalent bonds, not ionic. And so this one's now got 4 sticks coming out. This carbon's already got 4 sticks coming out. So it won't be bonded to any hydrogen, and this one now has got 4 sticks. And don't forget, we should throw in some hydrogens there at the end of those bonds. But if you catch me not putting any hydrogen at the end of any bond, covalent bond, it's just assumed that that's hydrogen. When we don't include the hydrogens, it's just known as the skeletal chain. A simpler, easier way to draw the structural formula. Well, you might have heard the term saturated and unsaturated fats in relation to the types of oils that you have in your diet. Well, you come across the same term, saturated and unsaturated, in organic chemistry when talking about hydrocarbons. Here's an example of a saturated hydrocarbon here and an unsaturated hydrocarbon here. What do you think the difference is? Well, a saturated hydrocarbon, such as butane, has the maximum number of hydrogen atoms attached to the main chain. In the case of butane with 4 carbons, it contains the maximum number of hydrogens, which in this case is 10. You might remember last year that the general formula for alkanes is CnH2n plus 2. Saturated. But whenever there's a double or triple bond, the hydrocarbon is unsaturated. In this case here, we've still got 4 carbons, but there's only 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. That's less than the maximum number of 10 for butane. And the general formula for an alkene is CnH2n. Might have remembered that from last year. So this one here is but-1-ene. At the bottom of page 221, it talks about this word, locants. And it's just simply a way of numbering the main chain carbons. We can number this main chain carbon with 1, 2, 3, 4, 5. So this is carbon 1, this carbon is carbon 2, this is carbon 3, 4, and 5. And so whenever it's pretty handy to have these locants whenever we have multiple bonds in the molecule, and a multiple bond being either a double bond or a triple in this case, or a triple bond in another case. But let's begin to name this one. This has 5 carbons, so it starts with pent. Now, it has a double bond in it, so it's unsaturated. And this double bond is located in the first possible location. It could be located here or here. So it's in the first locant, we say. So this would be pent-1-ene. Ene because of the presence of the double bond. So in the name pent-1-ene, to indicate the location of the double bond in this case, but if it's a triple bond, it would be pent-1-ine, of course. We have, on either side of the number, we have a hyphen. Once upon a time, just historically, for historical reasons, I'll say this would have been one pentene. That's still correct, but it's more correct to put the 1 just before where you need it in the molecule. The 1 indicates the presence of the double bond. We're up to page 222 now, and we're about to look at hydrocarbon substituents. Now what's a substituent? Well, let's have a look at this compound. It's got 1, 2, 3, 4, 5, 6 carbons in its parent chain, in the main chain. Or is that the main chain? Let's have a look, because there's another carbon here. 1, 2, 3, 4. Now that carbon can't be in the main chain, because the main chain is the longest continuous carbon chain, and it's this one here that's the longest continuous one. Oh, hang on, let's go from this way. 1, 2, 3, 4, 5. Now that 5 that way, 4 carbons that way, but no, 6 across this way. So the longest continuous chain of carbons, the main chain, is this one here. So let's look at what this one is. This little side branch, as we often call it, is a substituent. A substituent is a side branch that branches off the main chain. And this substituent is a hydrocarbon itself. And so a substituent that's a hydrocarbon with one carbon is called a methyl. Meth, because it's only got one carbon. Remember the prefixes from before? One carbon's methyl. And the YL on the end, the suffix YL, indicates that it's a substituent, a side chain. So any side chain that's a pure hydrocarbon ends in YL. So this methyl is starts with METH. It's only got one carbon. If it's got 2 carbons, if the side branch is 2 carbons, it's ethyl. And propyl for the next one, and butyl, but doesn't really usually go beyond that. So here we go, back to this one. So this methyl group here is located along the main chain. Now the question is the methyl group attached to the 1, 2, 3, 4th carbon, or the 1, 2, 3rd carbon? Well, the answer is to the 3rd carbon. You always number the main chain to give any substituents the lowest possible number. So we number it from right to left. 4, 5, 6. So this becomes 3-methyl hexane. 3-methyl hexane. So as you can see, just before the prefix for the substituent, you write down a number, and that number indicates which carbon on the main chain it's attached to. Whenever you have a number in a organic molecular name, the number is always separated by a letter with a hyphen. So 3-methyl hexane, substituents. Yeah. So let's have a look at this worked example here on page 222, I think it is. Yep, 222. It's got this pretty complicated looking molecule here. Let's try to name this hydrocarbon using our nomenclature rules. Okay, so first of all, let's try to find the main chain. Got 1, 2, 3, 4, 5 carbons this way. 1, 2, 3, 4 carbons this way. So that's the main chain going in a straight line along there. So it's got to be some sort of pent. The suffix, the prefix pent must be used. It's got a triple bond between carbons 1 and 2. So the name indicates the suffix "-ine" at the end somewhere. And it's a 1-ine because, as before we discussed, do we number the parent chain 1 to 5 this way, or 1 to 5 that way, from left to right or from right to left? Well, in this case, the most important aspect of this molecule is the triple bond. So we number it from 1 to 5 this way. So it'll be a 1-ine. Okay, so are there any side branches now? Well, yes, there is. There's this methyl group here. Methyl because it's an alkyl group that contains only one carbon. A 1-carbon side branch is a methyl. And don't forget the general name of these types of molecules is either alkanes, in this case alkyne, because it's got a triple bond, but if that triple bond was a single bond, it'd be an alkane. Alkene for a single bond. So the name of this molecule is, by the way, that methyl group is located along the first, second, third carbon along the main chain. So it'd be 3-methyl pent 1-ine. By the way, I hope the wobble factor's not doing your eyes in. I'm at a wobbly desk tonight, so we're up to page 223, and we're looking at the situation where you might have multiple substituents, like in this molecule. Step 1, you've got to find out where the main chain is. That looks a bit of a long chain down that way, so let's count how many carbons. 1, 2, 3, 4, 5. There's 5 carbons that way. There's 3 going that way. But there's 6 going in the straight way. 1, 2, 3, 4, 5, 6. So the longest continuous chain, remember, is the main chain, and it's 6 this way. So it'll be a and by the way, there's only single bonds in this molecule, so it'll be a hexane, something hexane. And so therefore, this one here, this hydrocarbon here, and this hydrocarbon here are both side branches. This one's a methyl group because it's a substituent containing only carbon and hydrogen. Methyl group, remember, any substituent that's a hydrocarbon ends in YL. So this must be an ethyl group. Okay. So the next question is, we know the main chain's going straight along there. But again, how do we number the locants? Do we number from left to right or right to the left? Well, just briefly, you always number, in the absence of a triple and double bonds, you number the substituents to give them the lowest number. So if we numbered from right to left, this ethyl group would be attached to number 4 carbon. That'd be number 5 carbon. But if we number from left to right, the correct way, that would be the second, that would be the third. We'll number them this way, putting the number inside the carbon. 4, 5, 6. So this is the correct way. You number according, that would give the substituents the lowest number. So this molecule here would be 3-ethyl, 2-methyl hexane. Now, why did I choose to place the ethyl group before the methyl group? Well, it's all to do with alphabetization. E comes before M, so the ethyl comes before the methyl. There's no space, there's no hyphen, there's no comma between the word methyl, the methyl word, and the parent chain hexane. That's what it is. 3-ethyl, 2-methyl hexane. What happens if we end up with 2 side branches that are exactly the same in a particular molecule, like we do here? And by the way, I've omitted all the hydrogen symbols just so that it doesn't look too crowded. Yeah, I have become a bit lazy here, but makes it easier to see. We have the main chain here, 1, 2, 3, 4, 5 carbons long. It's not along there or there because that would give us only 4 carbons. So that's the main chain. And if that's a main chain, we've got 1, 2 substituents, and they're both methyl groups. They're both methyl, and they just so happen to be attached to the same carbon, which you can have. So when this happens, what you add into the name is a thing called a multiplier. So this happens to be, by the way, which way do we number? 1 to 5, that from the left, or 1 to 5 from the right? Well, it doesn't matter actually, because the two methyl groups are attached to the third one anyway. So 1, 2, 3, 4, 5, that's the third carbon. So that would be called 3,3 dimethyl pentane, because there's no, they're all single bonds, no double or triple bonds. 3,3 dimethyl pentane. The multiplier is the di part, and both methyls are attached to the third carbon. 3,3, this one's attached to that. 3,3, two of them, so dimethyl pentane. If there were 3 or 4 methyls in this molecule, in the case of 3, it'd be trimethyl pentane. If there were 4 methyls, it'd be, It's tetramethyl pentane. If there were 5, happen to be 5, that'd be pentamethyl pentane. So multipliers. The next section on page 222 is this assigning locants examples. They give you 2 more examples of naming 2 more compounds, hydrocarbons, this one here and this one here. This one being 2,2,4 trimethyl pentane, and look, they just list the reasons why here. They give you a step-by-step rundown here. And this one here is 3-ethyl-4-methylhexane, and again they talk you through it here. Have a look for yourself sometime. We're running out of time here. So up until now, the main chain has been straight, like in hexane. But quite often the main chain can form itself into a circle, into a cyclic formation. We call these cyclic hydrocarbons. And so a cyclic hydrocarbon consists of a ring of carbons, and its name includes the prefix cyclo as a prefix. For example, this one here, cyclohexane, is a ring of 6 carbons, 1, 2, 3, 4, 5, 6. I haven't written the letter C at each of these corners, but at each corner of a cyclo type of molecule, you assume the carbon's there. So there's a ring of 6 carbons here, and in the case of cyclohexane, it doesn't matter what you number the carbons as, because each carbon's the same. The numbering really only comes in when you've got multiple bonds anywhere in the ring, or you've got substituents. Let's have a look at one now. Let's have a look at an example of a cyclohydrocarbon. Let's look at this psycho looking one here. There's a carbon ring here, and it's got 6 carbons, so it's got to be some sort of a cyclohex something. It's an ene because there's a double bond here. So it's got to be a cyclohexene of some description. And its actual name is 1-ethyl-6,6-dimethyl-cyclohex-1-ene. So let's go through that step by step. So the most important part, I'll use the top right hand corner of my little square pointer. So the most important part of the carbon ring is this double bond. So we number the carbons with the double bond at the lowest numbers. So that's carbon 1, carbon 2, 3, 4, 5, 6. So that's why, so what are the side branches? This side branch here has got 1, 2 carbon, so it's an ethyl group. And there's 2 more side branches, one there and one there, and they're both methyl groups because they've only got 1 carbon. This ethyl group's attached to the first carbon, carbon 1, so it's 1 ethyl. And these 2 methyl groups are attached to the same carbon, carbon 6. So that's 6,6. That's 6,6 dimethyl. So again, why is ethyl mentioned first? Because E for ethyl comes before M for methyl. And by the way, the multiplier di is not considered in the alphabetization situation. So yeah, if there's 2 ethyls, you just put the di there. So yeah, check out that one. Right, so anyway, I'd like to wrap it up pretty soon. You can read about aromaticity. Aromaticity is, or aromatic compounds, are cyclic compounds like this. And the most common aromatic compound is benzene. You've probably seen this, a famous symbol, probably because it looks a bit like a lock nut that you use with a bolt and a nut, but that's your cyclohexene. That's your benzene ring. This is the benzene ring, and that's another way of drawing the benzene molecule. Benzene is resonant, hence the inner circle there, and it's an inner circle because the 3 double bonds in the benzene ring are delocalized. They alternate, they resonate between that position. The 3 double bonds resonate from that position to that position. They go to opposite positions. But they're not so much double bonds. They've actually seen that those double bonds are all equally shared amongst all of the 6 carbons in the carbon ring. So it's more of a case of delocalization, not resonance. They're delocalized, they're shared equally to produce a really cool molecule. So anyway, it's time to wrap this video up. You're probably bored by now. Have a go at these questions. They're not very hard compared to the examples that I showed you earlier. Yeah, so what do you think of this COVID-19 situation, Mr. Pacey? Oh, well, I think it's not a bad scenario, Mr. Ed U Cate, because, sometimes we need a bit of time to ourselves, a bit of isolation. Oh, hi, guys. Sorry, I'm talking to Mr. Ed U Cate there behind me. He's still there. Anyway, that wraps up Chapter 9.1, the first section from Chapter 9. I hope that wasn't too long for you. Anyway, look, it's such a fascinating topic that I had to stretch it out as long as I could. Have a good one, guys.